Hi everyone, welcome back. This is our last lecture on probability, and in it we're going to do a couple of applications of discrete random variables. So here's the two applications we're interested in. One's known as the bins and balls problem, and it is suppose that we throw m balls into n bins. On average, how many bins would be empty? On average, how many bins would have one ball in it? And we can continue on that line of questioning. Now this is a problem that arises in hashing, and you'll see this in a course like CMPT 307. Another problem we'll be interested in is the coupon collectors problem. So suppose we have a bin containing many copies of n types of coupons, and we draw coupons one at a time at random. We're going to assume that each coupon has an equal likelihood of 1 over n of being drawn at each instant. And the idea is that that bin is full of coupons, so you're never going to run out of one type of coupon. You can effectively imagine there's infinitely many of each type of coupon in that bin. And we want to know, on average, how many draws will it take in order to get all n coupons. As an analogous problem, you can think of it as rolling a die. So if we're rolling a 6-sided die, how many times would I need to roll the die on average in order to have every number come up at least once? So that's an analogous problem. And so these two problems, we are looking at concrete versions of them, but they really do form classes of these kinds of problems in general. For example, the hashing problem might not be phrased as a bins and balls problem, but it is equivalent to it. And similarly for problems that you may encounter that can be cast in terms of a coupon collector problem, like the rolling the die problem. So let's first review some of the essential ingredients we're going to need for these problems. The idea is expectation is what we're going to be computing, so the expected value of a random variable. So we need to know one of the most important properties that we have about the expected value, and that is that it's linear. So before we get to that, we'll do a very brief review of what we did last lecture. So the first thing we did was talked about the probability of a certain value coming up for a random variable. So in that case, we had S was our sample space, big X was our random variable, little x was some value that the random variable can take on, so some value in the range. The probability of little x is denoted by PR of big X equals little x, and it's the sum of the probabilities of all the outcomes in the sample space that had value little x under the random variable. Let's look at an example. So S is the set of all binary sequences of size 3 bits. So these are length 3 sequences. Capital X denotes the number of 1 bits in the binary sequence. The range is just the values 0, 1, 2, or 3, because that's how many ones we could have, 0 ones, 1, 1, all the way up to possibly 3 ones. What's the probability that the random variable is equal to 0? So this is, what is the probability that if you take a sequence at random, that it has no ones in it? Well, the number of sequences that have no ones, we know how to count that. That's 3, choose 0. And that is going to be divided by the size of the sample space, and that's 2 to the 3. So we have our answer of 1/8. Now if you think about what ingredients we needed there, we needed to know what is the size of our sample space. That was 2 to the 3, or 8. We also needed to know our event space. Our event space in this case was the set of all sequences such that capital X of S, or the value of the random variable, is 0. And there's only one such sequence. If there's no ones, then they're all zeros. In other words, where are we going to put the ones? Well, since we're not choosing any ones, of the 3 spots, we're choosing none of them to contain a 1, and that's how we computed the size of that event space. Similarly, the probability that x equals 1, in terms of our event space, this is x of s is equal to 1, And so those consist of all these strings with 1, 1. So it's 1, 0, 0, 0, 1, 0, or 0, 0, 1. Of the 3 spots, we're choosing one of them for a 1, and that's all over 2 to the 3. So in other words, 3/8 is our probability here. Similarly for this one, x of s is equal to 2. If you're going to have 2 1s, they could be 1, 1, 0, 1, 0, 1, or 0, 1, 1. So there's 3 ways to get 2 1s, and that is equivalent to, of the 3 positions, choose 2 of them to contain 1s. And so we get our probability of 3/8. And lastly, x of s is equal to 3, means all 3 spots have 1s in them, and there's only one possible string. 3 choose 3 is our one possible string, and we get a probability of 1/8. In general, we could write down the formula, which says it's going to be 3 choose k all over 2 to the 3. If I write it in this way though, 3 choose k 1/2 to the 3, we can see that this is a binomial distribution. So this is an example of a random variable with a binomial distribution. And you can have a look at lecture 9 from last day where we talked about the binomial distribution. So now we want to focus on expected value. So let's review what expected value is. The expected value of a random variable is defined by the sum of x times the probability that the random variable is equal to x, where we sum over all of the values in the range. Equivalently, this is sum over all the elements in the sample space and take the product of the value of the random variable times the probability that that outcome occurs. So from the last example, we worked out the probability distribution for our random variable of binary strings of length 3. And now we can work out the expected value. So the expected value is, it's 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8. Or in other words, it's 3 plus 6 plus 3/8, which is 12/8, or in other words, 3/2. So there is our expected value, which as a decimal is 1.5. So how many 1s do we expect to get when we pick a random binary string of length 3? We expect to get, on average, 1.5 1s. So somewhere around 1 to 2 1s is what we would expect. Now, could we have gotten this a different way without having to go straight for the formula? The answer is, yeah, we did make the observation that this was a binomial distribution. So if we go back to lecture 9, when we look at the summary of the binomial distribution, we see that our particular example for our random variable is n equals 3 and p equals 1/2. So our probability that x is equal to k was 3 choose k 1/2 to the k. And in this case, the expected value should be n times p. So we would expect that the expected value, so we would get under this summary that the expected value of our random variable is n times p. N is 3, p is 1/2, so we should get a value of 3/2. And that's what we did get straight from the formula. So the idea was, if we can make an observation that our probability distribution is binomially distributed, or geometrically distributed, then we already have computed the expected values in those cases in general, so we can use those results as well. As an alternative, I just want to show you that we could use the other formula in the definition. So we have used this first one where we summed over all of the elements of the range and took the product with the probability that that value of the random variable occurs. That was our sum right here. But we could also use this form as well. And so what would that be? That would be saying sum over all of the elements of the sample space and multiply by the probability that that outcome occurs. So here we are going to sum over all elements of the sample space. Well, what is the probability that a single element of the sample space would occur? Well, all strings occur with equal likelihood. So that's 1/8 in all these cases. So this becomes the sum of the random variable of s for s over all elements in the sample space times 1/8. So in other words, it's 1/8 times, and we have x of, and then we just go through all of the elements in our sample space. So x of 0, 0, 0 plus x of 1, 0, 0 plus x of 0, 1, 0 plus x of 0, 0, 1 plus x of 1, 1, 0 plus x of 1, 0, 1 plus x of 0, 1, 1 plus the final one, x of 1, 1, 1. See if I got them all. 1, 2, 3, 4, 5, 6, 7, 8. Yep, I've got them all. And so then the value of the random variable is 0, 1, 1, 1, 2, 2, 2, and 3. So that is 1 plus 1 plus 1, so 3, 3 plus, and down there is another 6, plus another 3, so that's going to be 12, so this gives us a value of 12/8, or 3/2. So that's just an illustration of how we could do the expected value calculation using that form. Now here is one of the most important properties we have about expectation. Expectation is a linear function. That's what these two properties are saying. So if x and y are two random variables on the same sample space, and a is some real number, then if I form a new random variable, a times x, which just gives me the value of the old random variable and multiplies it by little a, then the expected value of that random variable is just little a times the expected value of the original random variable. Also, if I took two random variables x and y and I add them together to get a new random variable, then the expected value of that new random variable is just the sum of the expected values of the original ones. We could summarize this by saying e of ax plus by is equal to aex plus bey. And then we say in this case that e is linear. So e is a linear function on random variables. So let's prove this. Let's prove that it actually has these properties. So in the first case, we want to show that e of a times x is a times e of x. So we'll just go ahead and use the fact that the expected value of this random variable is the sum over, and here I don't want to sum over all the values of the range because the random variable x and the random variable a times x probably have different ranges. So instead of using this form of the expected value, I'm going to use this form to compute the expected value. So there I sum over the sample space. So we're going to sum over the sample space, and for those values in the sample space we will take the value of our random variable at those values of the sample space times the probability of that value in the sample space. And now I go to work on this part right here. Ax of s, that's equal to a times x of s. So that's what a scalar multiple of a random variable is. A times x is just take your element of your sample space, evaluate your random variable x at it, and then multiply the result by a. So that means this can be written as a times x of s times the probability of s. But now I can bring that a out front. And so this becomes a times the sum of s in s, x of s times the probability of s, and that is exactly the expected value of x. And it's got that scalar a in front. So there we go. We've just proven the first part. For the second part, we can do the same thing. We give x plus y is equal to the sum over s and s of x plus y evaluated at s times the probability of s. But that's the sum over what is x plus y of s? That's equal to x of s plus y of s. And so that becomes x of s plus y of s times the probability of s. And now we can distribute the probability across that sum. So that becomes x of s times the probability of s plus y of s times the probability of s. And that's just the sum of each of those two individually. So that becomes the sum of x of s, probability of s, plus the sum of y of s times the probability of s. And that's just the expected value of x plus the expected value of y. And there we go. We've just proven the fact that the expected value is a linear function. Now the proofs weren't that challenging. They were actually pretty straightforward. They're right from the definition. So the fact that the expected value is a linear function of random variables comes right from the definition. Now it turns out that this is quite a powerful result. Let's have a look at a previous example we've done. So if we go back to the binomial distribution from last lecture, here we were looking at the particular case of a coin, a biased coin that was tossed n times. We wanted to count up the number of heads, or the expected number of heads we get in n tosses. And when we did that, we ended up getting this sum we had to evaluate, and that took a little bit of work. We had to try to recognize it coming from the binomial theorem. But now I'm going to show you the power of using the linearity of the expected value function. So here we'll call this an alternate solution. And we'll say it's using linearity of the expected value. So how are we going to set this up? Well, the idea is we need to write the random variable that we want to compute the expected value of as a sum of simpler random variables. So what is the random variable we want to deal with? Well, it's the one we've defined above here. It was what we called h, and we'll scroll all the way up. And what does h do? H just counts the number of heads in a string of n coin tosses. So what we're going to do is we're going to define a new random variable, hi, for each I between 1 to n. And what it is hi just returns 1 if the ith toss is ahead and 0 otherwise. So be the random variable that gives 1 if ith toss is a head and 0 otherwise, so if it was a tail. So what do we have now? Well, then h, this is the one that counts the number of heads, that would be just h1 plus h2 plus all the way up to hn. So we could write our original random variable we're interested in terms of the sum of these new ones. And so the expected value of h is the expected value of h1 plus the expected value of h2 plus all the way down to the expected value of hn. And that's by linearity. So that's because e is a linear function. Well, that's just asking what is the expected value of h1. h1 is either going to be 1 if it's ahead or 0 otherwise. So what is the expected number I would get for h1? Would I expect a 1 or would I expect a 0? Do I expect it to be heads or do I expect it to be tails on the first toss? What about the second toss? What about the third toss? Well, all those expected values are going to be the same because they're all just about what is the expected value for a single toss of the coin. There are n of them here, so this would be n times the expected value of any one of those. So we'll just say e of h1. What's the expected value of h1? Well, now we can go ahead and say, well, h1 has range 0 or 1. So we'll just work out the value of it using the formula. It's 0 times the probability that h1 is 0 plus 1 times the probability that h1 is 1. This is 0 because it's 0 times, it doesn't even matter what the probability is, it's just 0 times it. What about this? Well, the probability that h1 is 1. What's the probability that you get a heads on one flip? Well, this was p. And in this particular case, I think it was 0.7 because it was a biased coin, but it was p nonetheless. And so this has a value of np. So the expected number of heads we would get if we tossed the coin n times would be n times p. You can see that that's what we had below. We got this one using the formula for the expected value on h and getting this sum that we ended up having to find the binomial theorem in there somewhere. On the other hand, if we use linearity and break h down into smaller random variables that are more simple to deal with, then we get it in a much more straightforward fashion. But we get the same result. So that in essence shows the power of using linearity of e. So we're going to use the fact that e is linear in these next two examples as well.